Today, I have the pleasure of introducing Michael. So Michael is a postdoc at RPL of the KTH Royal Institute of Technology in Sweden, in Stockholm, Sweden. He was also a PhD there at that very same lab under the supervision of Danica Kragic, Anastasia, Varava, and Hung Yin, where he conducted his research exactly on this, on how can we learn representations that are actually structured and that allow efficient robotic manipulation. And I think, as he said, he's also organizing an micro workshop on exactly this kind of topic. So if you are interested, check it out. It's going to be very soon. And having said that, Michael, please take it away.
Right, thank you very much for the nice introduction. Gonna then start with my slides. Can everybody see them? All right, perfect. Okay, then, yeah, welcome. My name is Michael, as introduced, and I'm going to talk about structured representation for robotic manipulation. First, a quick overview of what this talk will contain. First, I'm going to make the point why representation matters, and then argue for the need for structure in certain kinds of representations. And then I'm going to dive into my own work that I did with my colleagues during my PhD and also pursuing now, which is mostly about our work in the Latent Space Roadmap for object manipulation with a focus on deformable objects. And I'm going to wrap up with a summary afterwards. Right, so why do representation matters? So here's a typical scenario that you have every day. You have two robots holding a deformable object, here a KTH hoodie. And now we are kind of tasked with, okay, what do we want to do with it? How do we represent? How do we control? How do we fulfill any meaningful tasks? And there are basically two principal ways from two sides we can approach this problem. One side is, I would say, more the classical way, where we really model every single aspect of the system, object, manipulators, and then we feed all of this in a very complicated controller, and that's the way we control the robot itself and achieve the desired task. So this is very difficult for the deformable object because their degrees of freedom are basically infinite. We know the kinematics and dynamics of the manipulator itself, but estimating it for the deformable object or the hoodie or clothing item is quite a different story. So on the other end, we have the learning approaches where we say, okay, let's just not do any representation handcrafted. We forget that we know how the robot looks and how it moves, and just feed in the image directly into big neural network, and then directly go from image to join commands. And there have been quite some impressive work on this, but also on the left side as well. As usual with things, I argue that we should be somewhere in the middle. And so we should still make use of the models that we know, or impose basically our domain knowledge into the problem, while still making use of these advances in the learning community to get the best of both worlds. So my talk is titled Structured Representation for Robotic Manipulation. Therefore, I first want to motivate why we even need the structure in our representation. So to answer this question, we start by what is actually a good representation. So because it's quite tough to define, okay, what should this representation contain, entail, and how do we define even what's a good and bad representation in the first place? For that, we can look to the related work. There are two quite recommend works on this topic that make a deep dive into this. It's from Lesort et al. And Burma et al., where they came up with kind of wish list for representations, especially for the concept of for control. And the first point on the list is that a good representation should be a Markovian. Furthermore, we want to be able to represent the true value of the current state with the representation well enough that we can perform policy improvement. So this is a bit more vague-ish, but it's basically that, yes, the representation should have close enough to the true underlying state that we can actually use it, and it's not random. Furthermore, we want to be able to generalize our learned value function to unseen states with similar features, so that we don't nothing works anymore just because we see a slightly different state. So we want to have the generalization of the representation as well. And of course, especially in the robotics domain, we want to have them low dimensional for efficient estimation. So let's look at this example. So let's say we have the unobservable underlying state space, hidden states X. In this case, it's just that it's if these blocks are L-shaped or they're square-shaped. Now we can have this underlying state can emit multiple different observations. For example, we observe the state with images, and we as humans can pretty much immediately see that these both are L-shaped, so they are the same underlying state, while these are also the same underlying state, being though a different one from the L-shaped one. So when we have now our mapping function C here, we want to map those into this corresponding underlying state. But as we can see, the observation itself are quite difficult. So now, of course, we can try to handcraft this state detector, but then we are limited to this single task, and we can only really do boxes. So for that, we kind of map it into some kind of latent space, here donated set. And we observe that this mapping will map all of them into an individual representation set. And then later, a downstream task, here denoted with FC, then performs the inverse mapping of here that does the many-to-one mapping back to the true underlying state. So now I'm going to argue for this set representation a bit more, and why the structure is important there. For example, here, let's assume we have two different mapping functions, and different mapping function obviously results in a different structure in the latent space. For example, here we have C1 resulting mapping these different observations of the same state in this configuration, while C2 maps it in this configuration. So it's not hard to see that there's a difference. For example, on the left side, we have them linearly separable, and on the right side, they are not. So now our insight we can draw from that is the more structured a representation is, the simpler a downstream learner can be. For example, if our task would be differentiating between these two states, so we can have, especially with the modern neural network, a classifier that works on both. But the weak classifier would only work on the left side, and we want to have it as simple as possible, because that's generally a good goal to aim for. So what would I add to this wish list of representation from Burma et al.? It is basically that good representation is one that is well structured. All right. So after I have convinced you all that representation should be structured, let me give some concrete example where we leverage this concept to actually do some object manipulation with in the robotics field. Our work is in visual action planning. And the goal of visual action planning is to giving a start and goal image to make a visual plan, which is a sequence of images showing the transition from the start state to the end state, as well as an action plan, which shows the action that needs to perform to transition between states. So here in this example, we have the shirt, and we want to fold it to this configuration, and we do this in 3 steps. By first folding the sleeves and then folding the whole thing in half. This work is based on the paper with my co-authors Martina and Petra, and is now conditionally accepted at transaction on robotics. So to get a bit into that, we start by talking about the mapping module, and here we try to impose this additional structure I was talking about. So what we can see on the right is the result of this additional loss function that we added to our variation autoencoder. So we feed in two images, and if the images are so-called action pair, we put them away from each other while we contract the no action pairs if they are the same underlying state. In this during the training, this looks like this, that the no action pair distance gets smaller and the action pair distances get closer to the DM value that we want. We found that dynamically increasing it works quite well, because it's important what kind of value you want to push them apart. If you push them apart too much, the structure gets not as favorable as if you push them slightly from each other. Therefore, we increase DM sequentially. You can see it here increasing. And then as soon as the gap is formed, we stop the increase and then keep training for, in this case, 500 epochs, so to get the desired representations. Now that we have this representation space, we want to basically perform planning in that, and for that we built a graph in the representation space itself. For that, we have the data set consists of pairs of images that are connected with the actions. So the data set only consists of not full rollouts of the task, but one task, a start task, and then a go task, and the action that was performed to get from one state to the other. We know it's a different state because, well, we performed the action, and the action is quite significant, changing the state. So that's one of the assumptions, that the actions in these scenarios are a bit more towards the task planning objective, like the pick and place action that significantly changes the underlying state, and not very small actions. With this reference graph in hand, we perform agglomerative clustering in the latent space and obtain this stepwise dendrogram shown here on the right. Now, in this dendrogram, you can obtain a lot of different clustering configuration by basically cutting at different tau values here indicated with the blue, green, and orange lines. Now we can see they result in different graphs. Here, as example, if we cut with tau 1, then we have 1, 2, 3, 4, 5, 6 separate nodes, clusters in this case, and four edges, and we have a disconnected graph as well, like 8 and 5 is not connected with the other guys. If we cut with tau 2, we get 3 clusters and 2 edges, and if we cut with tau 3, we get only 2 clusters and a single edge. So now we want to strike a balance between connectivity and basically how well we can traverse the states. So we want to not eat up too many states, because then we merge states that are different. But we also don't want to have disconnected graph components. To address this, we have added an outer optimization loop that basically optimizes the number of edges with a maximum number of the connected components that can be set as a hyperparameter. So given this now clustering, we built the edges with the reference graph in order to connect the different nodes. So now we have a graph where each node represents a state, and transition is allowed transition from our data set to another state. And now we can basically perform visual action planning by encoding a new novel state and then following this graph to where it might lead. One thing to consider here is that because VIEs try to make a smooth representation, there are states in the middle that, especially for these more discrete actions like moving blocks, are actually non-sensible states indicated here. So with this method, we transition from one state in the other state that we have seen, and we are kind of sure they exist, while we avoid just linearly traversing the latent space, which results in states like these boxes here, where there's half a box here because it's at the point of moving mid. So these nonsensical states are avoided. To summarize this one more time, so first we have a variational autocoder to capture the system global structure and dynamics of the whole task. And each node is then associated with a region of discovered states that we know, and that's one node, and we can represent it with with a single underlying state. And each edge is associated with a possible transition between these states. And therefore, we very easily can plan along the graph in the latent space and then decode the representation of the underlying state with the decoder and then obtain the visual plan. Now, for the action planning, now that we have the latent space, there are many options to address this. One option we went for is to have a simple MLP where you feed in the start and goal state and then obtain the action that connects them. So that's a supervised learning problem and was quite successful. Another option, we can also integrate this action directly into the LSR itself by averaging the actions we merge with the different edges that build later the connection itself. That's also quite successful, and this depends a bit on the task and domain you want to use, which is more appropriate to go for. Now, we tried this in 3 different domains. We had the rigid task where we had this box stacking task with quite similar looking boxes where we feed in the start and the goal state. Then we have this generated visual plan. And here the blue and green circles are indicating the action plan where it picks at blue and releases it, or the opposite. Yeah. So it's the opposite, it picks at green. And then you move that over there. We had the hybrid task where we had these 2 boxes connected with a rope, and it moves the box in this grid here. And then the rope can get stuck on these pillars, and then you have to pick the rope indicated with this rope color over the pillar itself, and then you can keep moving it into the desired target condition. You can see that these middle images are a bit blurred because they are actually reconstructions from the VAEs and not from the training data set. And the states, start and goal states, are also novel states from the same distribution, but not seen by the model during training. And finally, with the deformable object here, you can really see that the reconstruction omits a lot of detail, but still preserves the overarching pick and place for the shared folding task. Now, to see that in action on the real robot, there's a short video here where we first compute all possible visual action plans, and then we pick one, and then we perform the action. And then when we do a replanning step, now we have different visual action plans that we have to choose from, and continue this until the goal is reached. So now there was only one plan left because now you don't have any way of reaching the state other than combining, other than following the plan here. So I'm just going to play this again because this was a bit fast. So we have this. This doesn't work. We see. I can pause it a bit. So here are a number of visual action plans, and they all kind of lead to the same result. There are different paths found on our latent space roadmap graph from start to goal. And then here you can see, okay, he first wants to fold this leaf, then the other sleeve, and then on the side, and then this the tiny edge here. And so he performs the first folding, and then instead of following the plan open loop, he does a replanning step where he takes the new current observation and redoes this procedure to arrive at the new goal state. And so the goal state is the same, but every time it gets a new current state, it replans it. So now it put the other sleeve up and still continues to go here. And once the one sleeve is fixed, there's only one feasible path that it found that it can follow, and that's exactly what he does. So he folds it over the side, and then he finishes it up with folding this leftover piece to here. Now it's close enough to the goal state, so they found the same node. One more. Oh. Yeah, they found the same node, and therefore the procedure terminates. So that was a quick overview about this work of the Latent Space Roadmap for object manipulation. And to recap, first, we impose a structure in the representation space using our additional loss function for variational autoencoder. Next, we cluster the underlying states. And then we connect these clusters using the action information from the training set. And then we use this latent space roadmap for visual action planning. Now, the structure depends heavily on the available training data, because we are reliant on the information if we have an action pair or a no action pair, basically if it's a similar or a dissimilar pair, so that our contrastive loss can push things away or attract to each other. Therefore, in this most recent work that we now submitted to IROS 2022, we considered this visual action planning with our LSR framework in the view of data scarcity. So what happens if you don't have as much data as you kind of need? And can we address that? Because the structure depends on the training data, the clustering depends on the structure, and the planning performance depends on the clustering. So we kind of want to address the case when we have not as much training data as we previously assumed. And for that, we came up with a paradigm we call Augment-Connect-Explore, or ACE for short. And the basic idea is that you augment your existing data to get new pairs. For example, you have a pair that is the blue to the green, the blue to the purple, and the purple to the green state as an example. And if you would build a graph out of that, it could kind of look like this. However, we can gain additional pairs if we would just know that these guys are actually the same underlying state. We don't have this label, we only have pairs. So we don't know these guys are the same state, but with an augmentation method, we might be able to get those and get additional pairs basically for free from existing data sets. Now next, we can only connect states in the LSR where actions connect them in the training data set. However, if they are not there, we cannot connect them. For example, in this example, if we don't have the connect step, we would not get the connection from this guy to this guy down here, because it's not in the training data. But this is still a potential valid connection that would us help to execute the plan, even with fewer data. And then we also looked into the explore phase, which basically considers, okay, how could we explore once we knew, okay, now we need more data, but we want to be most efficiently into exploring it. Like, which data is most valuable for us? For that, we augmented our already large framework with 2 additional models. Luckily, they are both completely offline, and one is the suggestion module, and this is given an image, suggests possible actions for that state. The other one is a latent prediction model that, given latent states and action, predict goal states. So now, the latent prediction model could basically solve the task, but you will never get it to train that well that it actually does this. So if you have enough data, you can probably just train a transition model that does, given current state, and an action gives you the perfect goal state. That was one of the first things we tried in the previous, and that doesn't work for the amount of data and the tasks we are considering. However, you get kind of close enough guess, so to speak, that it can be used to do the phases augment, connect, and explore. Before I'm gonna dive into those, I just want to shortly explain the suggestion model a bit more. So the suggestion model is based on 2 core observations, and that is that several valid actions can be applied to the same state. So there is not a unique one action per state, but you can have multiple actions. Like here, we can have this block, or we move this block, or we move this block. So there are 6 different actions for this state as an example, but also the same action can be applied to different states. And so you can move this block up here, but you can also move it if another configuration is here. Maybe it's easier on the shirt. For example, in this case, the arms are folded in a cross, and you can move this, can make this move, but you can also make this move if the arms would be folded in a line here. So the suggestion model wants we want that it gives us the potential actions that you can do on a given state, and we combine this with the latent prediction model to basically perform this augment step, where we build new similar pairs based on demonstration ones that are built, and two observations are assumed to be similar if the same set of actions lead to the same underlying state. So how do we do this? We take an underlying state and we ask the suggestion model, please tell us what kind of actions are you actually proposing. Then you get the set of actions. For example, you get all 6 actions for the block example, and then you try to take another state and ask the same. Okay, give me the actions of those. So, and if applying the actions to the state for both cases result in the same target states for all the actions, then we assume that the state is actually the same. So this worked quite well for the box stacking task. We didn't get that many new samples for the folding task. Here's just one example. We consider them all the same underlying state, and it connected now another one. So this image is actually different. Without knowing beforehand that those were also the same state. So we increased the data set size. We use a similar concept for the connect step. And so we want to build these connections or shortcuts between nodes of the LSR that are able to traverse, but not in our training data set. And therefore, we again use the suggestion model first and see where, if we apply the latent prediction model, where we end up. And if we end up close enough to already known or covered node, then we say we can safely build a shortcut and assume that this is also a path that the method can take. And lastly, for the explore, we want to have target exploration action that are proposed. So in here we kind of invert the thing. We also suggest, okay, give me a number of potential action, and then we perform the one that results actually in the furthest away prediction of the latent space from any known state. Therefore, we try to get the action that is most unexplored. So here, for example, it noticed that if it would perform the action from down here to up here, this would be a very novel state because it's far away in its representation space from anything else. And then it adds this new pair into the data set. Now this can be a bit counterproductive depending on your task, but it also gives you the opportunity to actually explore completely novel folds by basically not following your data set where you might have more sensible folds where you fold either cross or up, but you not fold the intersection between. And the exploring model noticed that, hey, there's a really unexplored area here. This might be interesting and very valuable information to have. And then we add this data also into our data set and train the method again. And then how does this perform in practice? Like what are the actual scores? So here we see one big diagram where we compare the original without the ACE LSR with the ACE LSR, and this was on the box stacking task. And we can see here at the T100, this is basically the original dataset size, which was 2,500 pairs. So here the performance is basically identical because when we did it with the last, we kind of increased the dataset size until it worked. And that was the number we ended up with. Now we kind of see, okay, but how, at what point can we now do sensible performance? So if we have only 80%, 75%, 60%, or even just 30% of the original data, can the ACE LSR still perform So it doesn't reach the end performance except for the 80%, but we can see that it clearly improves the performance on the original one. Therefore, we conclude that this is a useful practice for visual action planning under data scarcity. We performed the same on the folding task on all 5 folds. Here we used 50% of the original data for our ACE model and applied this Augment-Connect-Explore paradigm in order to enlarge the data set. And we can see that compared to the original LSR, which only managed to succeed fold 2 and fold 4, and one lucky fold 5. So each fold was repeated 5 times, while the ACE LSR was able to achieve actually the same performance then that we achieved with the Epson LSR with 100% of the data in our first publication about this work. So summarizing and wrapping up my talk, structure is important. So please introduce structure to your representation. I also talked about the Latent Space Roadmap framework to perform visual planning to manipulate rigid or deformable objects. And I introduced our ACE paradigm to deal with visual planning in data scarcity settings. The 3 papers I talked about is the Latent Space Roadmap for visual action planning of deformed and rigid object manipulation, published in IROS 2020. Then our extension on that, the journal version with additional tasks and much more evaluation, now conditionally accepted at Transaction on Robotics. And then our now recently submitted ACE paper for IROS 2022. Let's see what the reviews say to that one. And that brings me to the end of the talk. And this work was mostly jointly done as a shared first author by me. So you can see the work with on my website, Martina Lippi's website here. She's a postdoc at the University of Rome. I think Uni Roma is the name. And then also Petra Poklukar, which is a PhD student here at RPL. So if you want to know more about this work as well as what my colleagues work on, please visit their website. And if you have any question, please don't hesitate to ask.
Okay, thank you so much, Michael, for the great talk. I think these topics of representation learning are quite important for robotics, because it allows us to give this interface between high dimensional observations and then actually what we want, which is robots to do something, right? And I think representation learning can be a very important step into getting that. I would just kindly ask you to stop sharing your screen. Perfect. So having said that, we are now open to questions. So if anyone has a question that wants to ask Michael, please go ahead. Okay. And Jinkia, you have a question? Go for it.
Yeah, Michael, first of all, like really great talk. I really enjoyed it. I have like a couple of questions, more on so like to understand it better. So my first question is, usually like you're doing clustering once you have like a latent representation, right? And once you do, like usually with clustering, especially for robotics, it can happen that you can have mode collapse, specifically for some particular task. For example, if you have like an obstacle avoidance scenario, and there are 2 ways that you can go around about the obstacle. It may happen due to some representation when you're clustering that it actually comes up with a policy to, rather than go either left or right of the obstacle to avoid it, just go straight through it. Did you guys see that kind of behavior happening in your scenario, like in the using your framework?
Yeah,
that's first.
I think I know what you mean. But and this is if you basically do like averaging, right? Like you have 2 paths and then you get a representation which is the average of the 2, and then you plan through it, and then it's right into the obstacle. With this method, this is not really concerned because we are building the graph in the latent space. So you would have basically 2 branching paths, and then when you plan on the graph itself, it would return just 2 paths. one left and one right from the obstacle. We have not done obstacle avoidance, but because we have the graph, that should be the outcome.
No, but aren't you like once you are clustering, right? Like it depends on the threshold at what abstraction level do you wanna cluster them together as like a single I would say node or single cluster. Is like, so do you think that can happen if we like if I reduce like increase the threshold to like really high value for clustering, then situation like this can arise, right?
Yeah. So if you cluster kind of the states left and right together, then you have a mixture of that state, and then it depends what your action prediction model makes out of that. So there it could be that you go like that you get the nonsensical state, but you might see it because you get the coding of the state and would look quite strange.
So yeah, I mean, I was kind of curious on that because this is like a known problem, and like usually when you try to add structure and like try to come up with like a more abstract representation. So do you have any thoughts on like first, like how can we actually choose a right threshold for abstraction? That's like one way, or other way would be like actually adding some kind of laws to have like this split, like basically maintain this split, even though we are going for a higher abstraction, but basically because this is like a safety critical application, or in some sense to avoid the collision, we want to have like a separate representation or separate cluster for them. Do you have any thoughts on how can we achieve that?
Yeah, so it's very true. Finding the threshold is quite challenging, and that's why we had this an auto optimization loop when we opted for basically a measure of connectivity, where we basically have we optimize the number of edges that are present in the graph, while having a upper bound on the number of disconnected components the graph is allowed to build. And that gave us quite sensible kind of thresholds where it cut the dendrogram to obtain the clusters. For how that translates to like to a motion planning obstacle avoidance scenario, there we have also the problem that it's a much more continuous task. So there some more modification might be necessary probably to this particular method.
Yeah, I mean, because I agree with the philosophy that you said, like adding structure is definitely helpful. And that's like one thing that would actually help us to generate intelligent robots. So like a counter argument for that usually is like adding structure is basically adding bias, right, to the learner that we have. That like in this particular case kind of act as an adversary for like in some particular corner case that can be like that do more harm than like help us. So
no, I mean, so that's basically the trade-off, because I mean, so we did before the advent of deep learning, we were quite adamant about handcrafting every possible feature, and that can, as you said, that can lead to quite some problems, because it might be that there's a better thing and we should let the network decide. But and that works especially for vision tasks very, very well, like letting the network basically extract the relevant features on its own is much more successful than SIFT-SURF or more older methods for object detection and recognition. So for robotics, I think it's going to the end-to-end extreme is not the way to go, because we actually know we have relevant domain knowledge that we can incorporate. We don't need to relearn the forward and inverse dynamics of our robot, for example, because we know these things. Like, so I agree there is a danger with adding too much bias and then basically undermining the potential benefit of the network. But adding none kind of makes the problem too difficult. And this we see this in the reinforcement learning setting. While the results are quite impressive, they are still very much data hungry, and deploying them on real robots is still a risky business. So that's why I'm arguing for like the middle way.
Yeah, no, I agree. And I feel the same way. It's like adding structure should help in like reducing this requirement of really high amounts of data for training. So do you have any thoughts on like the structure that you mentioned? Like there are different representation that we can work with. Like even for, let's say, orientation, we have like 3 or 4 different representation based on the community that you talk about, right? So what do you think is like a good, I mean, you specify that we need good representations, right? Like, so what is your definition of good representation?
Yeah, so it's basically what the related work had, with the edit of that one that has a useful structure to it. Like, and it is vaguish because it will still depend on the task. Like there are some like you can also have structure like imposed by the geometry of the space itself, like that can be exploited. Not everything has to be in Euclidean space and stuff like that. But that very much depends on the data and the task. So that is a inductive bias we choose as we still choose. And I don't think there is kind of a way of defining what is the best possible structure for all possible tasks. It's similar to when in the related work they define what should be good representation. It's one that you can use to improve your policy. Like, this is true. It doesn't give you that much. It kind of gives you the right idea, but it doesn't give you you can't nail it down much more because of this problem that this still depends very heavily on the task.
Yeah, thank you so much. In the interest of time, I will let others ask questions as well. Thank you.
Thank you.
I really enjoyed your talk.
Thank you, Enrique, for the questions. Are there more questions in the audience about Michael's work? You can raise your hand. Okay, Alberta Longini, do you have a question?
Yes, thanks, Michael, for your talk. As you were talking about these models being data angry, I guess that as you showed just t-shirts, if you try and use your representation to fold a pair of pens, let's say, this wouldn't work, right?
Yeah, no, it would not, because they are completely out of distribution.
Exactly, and because probably your model has never seen this data, so it's not possible. But then once you learn this structure in your latent space for folding, okay, that it's a t-shirt and it has some specific shapes, but do you think that there is a way to use and transfer this structure to other type of or other shapes, for example, instead of like relearning everything, to use the structure that you learned and transfer it in other shapes, other type of objects, other tasks?
So I mean, there we have to kind of, there is work with that tries to make basically more general representation space as possible, but it depends very much on the downstream task. Like there is this the model from Facebook on the Instagram data set, which is unsupervised representation learning model, and that's the Instagram data set is 1 billion images, and it tries to impose basically a contrastive structure into that space so that you then can use it for most things. So we actually tried using a similar approach from this one from Google for it's called SimCLR, to see how that works if you apply it, for example, just on the boxes, and that doesn't work. Like having this the information of similar and dissimilar pairs really helps the structure, but then how to transfer this structure to another space without reorienting, like reorganizing it, that might be difficult. Like you kind of would need another mapping to do that, and then you might just can do the mapping in the first place. Maybe you can have a more abstract representation of the data. So if it is for folding, you don't need images. You might deal with other representation like graphs.
Okay, interesting. And what about finding a hierarchy of like semantics, maybe like action, moving a corner or moving an edge or moving a sleeve or something that has a specific shape, but in not anymore the semantic of t-shirt, but sleeves or
yeah, so there is some
body.
interesting work towards exploiting natural hierarchy in data with using hyperbolic spaces, I think. That's not quite there yet. Like they haven't really shown that convincing results, but that is kind of getting the natural hierarchy in the data into the representation is definitely an interesting direction.
Okay, thanks for your answers.
Thank you so much for your question, Alberta. Are there any more questions in the audience? Okay, Ali, you have a question. Please go ahead.
Yes, hello. Thank you, Michael, for this talk. It was really nice. I just have a small question. You are trying to generate like a representation for like to achieve like target or goal state. I saw like at the end that most of the goal state that they have like for folding the t-shirt, it has like specific like form. Is by like changing this target state or not the target state, like the shape of for the t-shirt, like maybe some rotation or maybe small way, if the representation will be different or not?
Yeah, so that depends on the amount of change. Like so if so because it's a t-shirt, they will be every time it's a bit different. So there are only that many ways to fold a t-shirt, kind of, and then you run into limitation of how much the robot can actually fold, like how small can you do it. So we didn't really investigate the rotational invariance for that. That might be a nice thing to add. But I'm very convinced that if you would change the color, for example, they would break because it's too different. So that is also something to. So the current approaches of that, one approach is just make it invariant to changes by basically varying these factors and saying, okay, let's just train it with all possible colorful things. That's another thing kind of to address for it. So how we collected the data was mostly we had a teleoperation of the robot, and we did the folding and then just always collected the pairs, and we didn't use the full rollouts.
Okay, thank you for this. I have another question, like during generating the states for achieving these tasks, if there is like some like fault that happens during this sequence of the states, is there like any correcting the state or something that you can like have small loop that can correct the state to continue achieving the task, or no?
Yeah, so it can kind of, because it's also a backstep, so the execution.
Yeah, can I be more specific? Generating, yeah, sure. Like I mean like structure representation. It is also like any float correcting state that may be happening during the sequence of the task of achieving the task.
I'm not sure I understand correctly. Like, do you mean that when you collect the data and then you have some kind of off data, how the method handles that, or what do you mean exactly?
But like during the robot, like achieving these task or this folding the t-shirt, there's some case that the robot failed in some state. Is there like any correction for this state? Can repeat this state or can fix this state to continue, so the robot can continue achieving the state?
So this depends on okay. So if it kind of it folds the sleeve and then it drops it halfway, is that what you mean? And then if it can recover from that? Yeah, in the current way, it cannot. If the drop is, it would continue from the closest state, it thinks it is. We have one project currently ongoing where we try to address this to some degree, where we have a higher level folding and then a lower level kind of fixing the state. But we also in this work didn't want to cover the entire state space, because that needs way more data. Like for there's in visual foresight planning, there's a good paper from that does this on the rope manipulation with the PR2. That's much more continuous, and the later version improved on that, but the earlier version was with 500 hours of video of self-supervised collection, like a huge amount of more data than we have, but we also don't have continuous tasks. So it's kind of like if this failure case happens, yeah, there is currently no way to recover.
Okay. Thank you so much. Really, it was a nice work.
Thank you.
So thank you, Ali, for the question. Unfortunately, we ran out of time. So I would like once again to thank Michael for the presentation. I think it's a very important topic. And now I would just like to very quickly share my screen once again, if I can find it, in order to, where is this? It's not here. Give me 1 second. So that we can just talk a bit about the next speakers of Talking Robotics. Yes, perfect. All right. So once again, thank you, Michael. I hope you can all now see my screen and my slides. Thank you once again, Michael, for the talk. It was an amazing talk. And in 2 weeks, we're going to have 2 speakers for the first time. So Elisa Massi and Lorenzo Vanucci from Sorbonne University. And they're going to be talking about animals and human brain mechanisms for robotics. So if you're interested in these kind of topics regarding neuroscience, please don't forget to attend. And once again, thank you so much for our sponsors, Animatus, Semio, and Paul Robotics, for providing us with the infrastructure that we need to actually conduct these sessions. And see you all in 2 weeks.